Most of Earth is hidden, not just unexplored, but unseen, beyond the reach of sunlight, beyond the rhythms that shape life on land. While coastlines feel familiar, and the surface of the sea seems calm and open, almost everything beneath it exists in darkness, cold and pressure that never relents. The deep ocean is not a single place. It is a vast layered world where time moves differently, where food arrives slowly, where life has learned to glow instead of grow leaves, and where survival depends on patience rather than speed. Mountains rise where no human foot has ever stepped. Plains stretch wider than continents. Trenches plunge deeper than the tallest mountains are high. Down there, sound travels farther than sight. Pressure reshapes biology. Creatures drift, wait, lure, and endure. Some live for centuries. Some have never encountered another of their kind. Many exist in numbers so small and places so remote that science still struggles to understand how they persist at all. Despite centuries of exploration, the deep sea remains one of the largest unknowns on this planet. New species are discovered almost every time a camera descends. Entire ecosystems appear where none were expected. Even today, the deep ocean quietly controls Earth's climate, stores its history, and reminds humanity how small its footprint really is. Tonight is an invitation to drift downward, to move slowly, to let curiosity replace urgency, and to explore 101 carefully chosen facts about the deep sea, each one a doorway into a world that exists beneath the surface of everyday life. Welcome to The Sleepy Scientist. If this gentle journey is helping you unwind, you're warmly invited to like the video and subscribe to the channel. And wherever you happen to be drifting off tonight, whether you're close to the rhythm of the ocean or as far inland as the world allows, feel free to share where you're listening from as rest slowly settles in. Over half of Earth's surface lies beneath ocean depths deeper than 200 meters, a fact that quietly dismantles the way the planet is usually pictured. Maps and globes tend to flatten the world into something neat and familiar. But beneath the blue areas lies a physical landscape far larger and more complex than the continents combined. Vast plains stretch for thousands of kilometers, smoother than many deserts. Mountain chains longer than the Andes rise from the seafloor unseen and unnamed. Trenches plunge downward to depths that defy everyday intuition, carved by the slow collision of tectonic plates. Geophysicists who study global seafloor maps often remark that if the oceans were somehow removed, Earth would appear dramatically rugged and scarred, far more extreme than its dry surface suggests. Land feels dominant only because it is where human stories unfold. In physical terms, the planet is overwhelmingly an ocean world, and most of its surface exists under conditions that humans never directly experience. The deep sea is generally understood to begin where sunlight fades enough that photosynthesis can no longer occur, a boundary defined not by a fixed depth, but by the behavior of light itself. As sunlight enters the ocean, it is steadily absorbed and scattered by water molecules and particles. Reds disappear first, then oranges and yellows, until only dim blue light remains. Eventually even that fades into darkness. At this point, plants and algae can no longer harvest energy from the sun, and a fundamental shift takes place. Above this invisible line, life is fast, energetic, and fueled directly by sunlight. Below it, energy becomes scarce, delayed, and indirect. Marine scientists often describe this transition as one of the most important ecological boundaries on Earth, even though it cannot be seen. Once sunlight ends, life must rely on material sinking from above or on chemical energy released from the seafloor creating ecosystems that operate under entirely different rules. When living space is measured by volume rather than surface area, most of Earth's habitable environment exists in the deep ocean rather than on land, a perspective that quietly reframes the scale of life on this planet. On land, life spreads across a relatively thin layer of soil and air. In the ocean, life occupies a three-dimensional space that extends downward for kilometers. From the fading edge of light to the abyssal plains below, organisms inhabit water columns, sediments, and rocky surfaces stacked one above another. This does not mean the deep sea is crowded in the way a rainforest is crowded, but it does mean that an enormous volume of space is available for life adapted to low temperatures, high pressure, and limited energy. Microbes alone fill much of this volume, slowly cycling nutrients and carbon over timescales far longer than human lifespans. Marine biologists often note that if Earth's life were judged by available living space alone, the deep ocean would dominate the picture, while land-based ecosystems would appear surprisingly shallow. It is often said that humans have explored more of the moon's surface than the deepest parts of the ocean floor, a comparison that reflects practical reality rather than exaggeration. The moon, despite its distance, is relatively straightforward to observe. It has no crushing pressure, no corrosive salt water, and no darkness that cannot be overcome with artificial light. Orbiting spacecraft have mapped nearly every crater and ridge in detail, and astronauts have walked directly across its surface. The deep ocean presents the opposite challenge. Pressure increases relentlessly with depth, capable of destroying unprotected equipment instantly. Reaching extreme depths requires highly specialized vessels, long preparation, and brief windows of observation. Oceanographers often compare deep-sea exploration to trying to understand a continent by peering through a handful of narrow windows scattered across vast distances. As a result, large areas of Earth's own surface remain known only through indirect measurements, making the world beneath the waves, in many ways, more mysterious than nearby worlds in space. Because of these challenges, the deep sea remains one of the least directly observed environments on the planet, not due to lack of curiosity, but because of relentless physical barriers. Darkness is absolute, temperatures hover near freezing, and pressure increases steadily with depth, placing constant stress on both organisms and machines. Cameras and sensors capture fleeting glimpses before returning to the surface, leaving scientists to reconstruct entire ecosystems from fragments of data. Nearly every expedition brings surprises. Familiar species appear in unexpected places. Entire communities are discovered thriving where none were predicted. Despite advances in robotics, mapping, and remote vehicles, the deep ocean resists comprehensive understanding. Researchers frequently acknowledge that much of what is known comes from brief encounters separated by vast distances and long stretches of time. The deep sea quietly reminds humanity that Earth is not fully charted, not fully known, and not fully understood. Taken together, these ideas reveal a planet far larger and stranger than everyday experience suggests. Most of Earth's surface lies hidden beneath deep water. Most of its living space exists beyond sunlight. Most of its landscapes and ecosystems operate under conditions humans rarely encounter. The deep ocean is not a distant edge of the world, but its central feature, shaping climate, biology, and geology while remaining largely unseen. To understand Earth fully requires looking not outward or upward, but downward, into a realm that continues to challenge exploration, patience, and imagination. Sunlight disappears rapidly with depth, leaving the deep sea in permanent darkness long before the ocean reaches anything that feels truly deep. Even in clear tropical water, light weakens dramatically within the first few tens of meters. Reds vanish almost immediately, followed by oranges and yellows, until the world turns blue and then fades altogether. By a few hundred meters down, sunlight has been reduced to a dim suggestion, and soon after that it is gone completely. This is not a gradual twilight that lingers for miles, but a swift transition driven by physics. Water absorbs and scatters light far more efficiently than air, and every additional meter increases the loss. Once darkness takes hold, it never lifts. There are no days or nights, no seasons of light and shadow. For most of the deep ocean, darkness is constant and uninterrupted, shaping every aspect of how life behaves. Marine scientists often point out that this absence of light is the defining feature of the deep sea, more influential than pressure or cold. Without sunlight, familiar cues vanish, forcing life to abandon surface strategies and invent entirely new ways of sensing the world. In this lightless environment, vision in the deep sea relies on extreme sensitivity rather than sharp detail, prioritizing the detection of faint signals over clear images. Eyes, when they exist at all, are often large relative to body size, designed to capture as many photons as possible. Instead of forming crisp pictures, these eyes function more like light detectors, tuned to notice brief flashes or subtle glows. Many deep-sea animals sacrifice color vision entirely, focusing instead on shades of darkness and light. Resolution becomes less important than awareness. Detecting the sudden appearance of a bioluminescent flash can mean the difference between finding food and becoming it. Some species possess eyes so sensitive that they can register a single photon, an extraordinary adaptation to a world where light is rare and fleeting. Others abandon vision altogether, relying on touch, vibration, or chemical cues instead. Researchers studying deep-sea vision often emphasize that it challenges human ideas of seeing. In the deep ocean, sight is not about clarity or beauty. It is about survival in an environment where information arrives quietly and without warning. For many deep-sea organisms, darkness is not an occasional condition, but a lifelong reality experienced from birth to death. Eggs hatch, larvae drift, and adults age without ever encountering sunlight. There is no memory of brightness, no contrast to compare against. Biological rhythms that rely on day and night cycles are absent or profoundly altered. Instead, time is marked by feeding events, chemical changes, or internal clocks tuned to entirely different cues. This permanent darkness affects behavior in subtle ways. Movement tends to be slow and deliberate. Sudden motion wastes energy and attracts attention in a world where hiding is often safer than fleeing. Reproduction, feeding, and growth are shaped by long intervals rather than daily cycles. Marine biologists have noted that many deep-sea species appear almost timeless, living at a pace that feels disconnected from surface life. In this environment, patience becomes a survival strategy. Darkness is not simply a lack of light, but a constant condition that shapes how organisms perceive space, time, and risk. In the absence of sunlight, biological light replaces it as the dominant visual signal in the deep ocean, turning darkness into a stage for brief, purposeful flashes. Bioluminescence is widespread in the deep sea, produced by chemical reactions within living tissues that emit light without heat. This light is not decorative. It serves clear biological functions, including communication, camouflage, and hunting. Some animals use light to lure prey closer, dangling glowing organs like bait. Others emit sudden flashes to confuse predators or draw attention away from vulnerable body parts. Counter-illumination allows some species to match the faint glow from above, erasing their silhouettes when viewed from below. The colours of this light are often blue or green, wavelengths that travel farthest through seawater. Scientists studying deep-sea bioluminescence frequently remark that it transforms darkness into a language of signals, brief conversations conducted in flashes and fades. In the deep ocean, light does not come from the sun. It comes from life itself, produced only when needed and extinguished just as quickly. Together, these ideas reveal a world where darkness is not an absence, but a defining presence. Sunlight vanishes quickly, vision adapts to scarcity, and entire lifetimes unfold without brightness. In place of the sun's steady glow, living organisms provide their own brief points of light, shaping a visual environment built on flashes rather than illumination. The deep sea is not simply dark in the way a room with the lights off is dark. It is a realm where darkness sets the rules, rewrites biology, and quietly governs how life sees, moves, and survives. Water pressure increases steadily with depth due to the weight of the ocean above, a simple physical truth with enormous consequences. Every layer of water presses down on the layers beneath it, and unlike air, water is dense enough that this pressure builds quickly. Near the surface, the effect is modest and easily tolerated by humans. A short swim or shallow dive feels normal, but as depth increases, each additional meter adds more weight, and the force becomes impossible to ignore. By the time the deep sea is reached, water pressure is no longer an abstract concept from physics textbooks. It is a constant, crushing presence that shapes everything from movement to metabolism. Oceanographers often explain pressure as the ocean reminding everything beneath it of how much water there truly is. The deeper one goes, the more the ocean insists on its own mass, pressing inward from every direction at once. There is no up or down to escape it. Pressure in the deep sea is uniform, surrounding organisms completely, and it defines the environment as much as darkness or cold ever could. At great depths, this pressure can exceed several hundred times that experienced at sea level, reaching values that are difficult to imagine without careful comparison. In the deepest trenches, pressure climbs to levels that would instantly crush unprotected human bodies or conventional machines. Every square inch of surface must withstand forces equivalent to the weight of large vehicles stacked repeatedly on top of one another. Scientists often describe deep sea pressure by pointing out that it is not sharp or sudden, but relentless and absolute. It presses equally from all sides, compressing materials, fluids, and even the spaces between molecules. For most familiar objects, this environment is utterly destructive. Air-filled spaces collapse, rigid structures crack. Even solid metals can deform if not designed correctly. Yet for the organisms that live there, this pressure is not extraordinary. It is simply normal. What feels extreme to surface dwellers is the baseline condition of life in the deep ocean, a reminder that habitability depends entirely on adaptation rather than comfort. Deep-sea life is built at the molecular level to withstand this constant compression, an achievement that reflects millions of years of evolution under pressure. Proteins, enzymes, and cell membranes in deep-sea organisms are structured to remain stable when squeezed. Chemical reactions that would fail under high pressure in surface organisms continue smoothly in deep-sea cells. Even the fluids inside these organisms behave differently, maintaining flexibility and function despite compression. Marine biologists studying deep-sea species often emphasize that these adaptations are invisible to the naked eye. There are no obvious pressure-resistant shields or armor. Instead, resilience is woven into the smallest building blocks of life. Muscles contract differently. Membranes remain fluid. Biological processes are tuned to function optimally in conditions that would instantly disrupt surface biology. This molecular fine-tuning allows life not only to survive but to thrive in environments that seem hostile by human standards. In the deep sea, pressure is not an obstacle, it is a constant companion. Because of this specialization, rapid changes in pressure can be fatal to organisms adapted to deep environments, even when other conditions seem favorable. When deep-sea animals are brought toward the surface too quickly, the sudden decrease in pressure can cause internal damage. Gases dissolved in bodily fluids expand, tissues rupture, cellular processes lose their balance. This is why many deep-sea species cannot survive capture, even if temperature and water quality are carefully controlled. The problem is not the surface itself, but the journey upward. Marine researchers have long recognized that pressure shock is one of the greatest challenges in studying deep-sea life. Specialized equipment is sometimes used to maintain pressure during ascent, allowing organisms to be observed alive under conditions closer to their natural environment. These efforts highlight how finely tuned deep-sea life truly is. Adaptation to pressure comes at the cost of flexibility, binding organisms tightly to the depths they evolved in. To explore these environments, submersibles must be engineered with extreme precision to survive deep sea pressure, pushing human technology to its limits. Every component, from hull shape to material choice, is designed to resist collapse. Rounded forms distribute pressure evenly, while thick walls made of steel, titanium, or advanced composites prevent deformation. Even tiny imperfections can become points of failure when surrounded by kilometers of water. Engineers often test submersibles repeatedly under controlled conditions before risking a deep dive, knowing that there is little margin for error. Windows, when included at all, are made from specially designed materials that balance strength and visibility. Life support systems, electronics, and instruments must all function reliably while compressed from all sides. Each successful dive represents a triumph of careful design and cautious planning. In this way, the deep sea does not yield easily to exploration. It demands respect, precision, and an acknowledgement that pressure, not distance, is often the greatest barrier to understanding the world beneath the waves. Together, these facts reveal pressure as one of the defining forces of the deep ocean, shaping biology, behavior, and exploration alike. The weight of the sea builds steadily, reaching levels that challenge both life and technology. Deep-sea organisms meet this challenge through molecular adaptation, while humans rely on engineering ingenuity to briefly enter their world. Pressure is not merely a background condition, it is an active presence, quietly governing what can exist, what can survive, and how far exploration can safely go beneath the surface. Deep-sea temperatures remain near freezing across most of the global ocean, creating a thermal environment that feels almost frozen in time. Once sunlight fades and surface influence disappears, water temperatures settle into a narrow range that barely shifts across vast distances. In many regions, the temperature hovers just a few degrees above the freezing point of seawater, regardless of whether the ocean above lies beneath tropical sun or polar ice. This happens because cold, dense water formed near the poles slowly sinks and spreads throughout the deep ocean, filling basins and trenches like an invisible blanket. Oceanographers often describe the deep sea as thermally conservative, meaning it resists change. Heat does not penetrate easily, and once cold water settles at depth, it can remain there for centuries. This creates a world where warmth is not just rare, but essentially absent. For life living under these conditions, cold is not an occasional challenge but a permanent state. Every movement, chemical reaction, and biological process unfolds in water that never warms, shaping a style of existence defined by endurance rather than activity. Seasonal changes barely affect conditions in the deep ocean, making it one of the most stable environments on Earth, despite the chaos that often plays out above. At the surface, oceans respond quickly to shifting seasons. Temperatures rise and fall, storms churn water, and sunlight varies dramatically across the year. None of this reaches the deep sea in any meaningful way. The immense mass of water above acts as insulation, absorbing and smoothing out surface fluctuations before they can travel downward. By the time surface disturbances fade, only subtle signals remain, often taking years or even decades to arrive. As a result, the deep ocean experiences no summer or winter, no sudden warming, and no cold snaps. Conditions remain steady year after year, century after century. Marine scientists frequently note that this stability is unusual compared to most environments on Earth, which are shaped by cycles and extremes. In the deep sea, consistency is the defining feature. Life does not prepare for change because change rarely comes. This remarkable temperature stability shapes slow metabolic rates in many deep-sea species, influencing how they grow, move, and survive. Cold temperatures slow chemical reactions, and in biology that means slower digestion, slower growth, and slower reproduction. Deep-sea animals often operate at a pace that feels almost suspended compared to surface life. Movements are deliberate rather than rapid. Growth can take decades. Some species may live far longer than their shallow water relatives simply because their bodies burn energy so slowly. Biologists studying deep-sea organisms often point out that efficiency matters far more than speed in this environment. With limited food arriving unpredictably from above, conserving energy becomes essential. A slow metabolism allows organisms to survive long gaps between meals and reduces the need for constant feeding. This is not a sign of weakness or stagnation, but of careful adaptation. In the cold depths, life has learned that lasting longer often matters more than acting faster. Cold conditions in the deep ocean also preserve organic matter far longer than in surface waters, subtly shaping the entire ecosystem. At warmer temperatures, bacteria and other decomposers break down organic material quickly, recycling nutrients at a rapid pace. In the deep sea, cold slows these processes dramatically. Dead organisms, sinking debris, and waste products can remain intact for extended periods, sometimes drifting slowly downward like a delayed echo of surface life. This preservation affects everything from food availability to scientific discovery. Organic material that would vanish quickly near the surface can persist long enough to feed scavengers or settle onto the seafloor. In some cases, remains can be preserved well enough to offer scientists insights into past ocean conditions. Marine researchers have found that cold temperatures effectively stretch time in the deep ocean, slowing decay and allowing matter to linger. This creates a system where nothing is truly wasted, only delayed, contributing to the deep sea's patient and methodical rhythm. These cold, stable conditions give the deep ocean its distinctive character. Near-freezing temperatures dominate across the globe, untouched by seasons and resistant to sudden change. life adapts by slowing down, conserving energy, and making the most of what arrives. Organic material persists longer, feeding ecosystems that operate on long timescales rather than rapid cycles. The deep sea does not rush. It endures, shaped by cold that never lifts and stability that rarely breaks, offering a striking contrast to the restless surface world above. Many deep-sea animals grow extremely slowly compared to surface species, a pattern that reflects the calm but demanding conditions of life at depth. In warm, sunlit environments, growth is often rapid because energy is plentiful and competition is intense. In the deep ocean, the opposite is true. Food arrives irregularly, temperatures remain near freezing, and energy must be carefully rationed. As a result, growth becomes a long-term process rather than a race. Some deep-sea fish add only tiny increments of body mass each year, while certain corals and sponges grow so slowly that a structure the size of a dinner plate may represent centuries of development. Marine biologists studying growth rings in deep-sea corals have found lifespans that challenge assumptions about how quickly life should progress. Slow growth reduces energy demands and lowers the risk of starvation during long gaps between meals. It also means that damage, once done, takes a very long time to repair. In the deep ocean, patience is not a personality trait. It is a biological necessity. Because growth is slow, lifespans in the deep sea can stretch for decades or even centuries, far beyond what is typical for similar species in shallow water. Fish that might live a handful of years near the surface can survive for many decades at depth. Some invertebrates, including certain corals and clams, may live for hundreds of years. This longevity is closely tied to cold temperatures and reduced metabolic rates, which slow the wear and tear that gradually damages cells and tissues. With fewer predators, fewer disturbances, and a stable environment, there is less pressure to live fast and reproduce quickly. Scientists often describe deep-sea species as existing on geological timescales rather than human ones. Individual organisms may outlive multiple human generations, quietly occupying the same patch of seafloor while the surface world changes dramatically above them. Long life in the deep sea is not about resilience to hardship alone, but about existing in a place where change arrives slowly and unpredictably. Limited food availability strongly favours energy efficiency over speed, shaping nearly every aspect of deep-sea biology. In surface waters, organisms often compete fiercely for abundant but short-lived food sources, rewarding speed, aggression, and constant activity. In the deep ocean, food arrives as a slow rain of organic debris, or as rare large carcasses sinking from above. There is no advantage to being fast if there is nothing to chase. Instead, success depends on minimizing energy use and being ready when opportunity appears. Many deep-sea animals drift rather than swim, glide rather than chase, and wait rather than search. Their bodies are often soft, flexible, and lightweight, reducing the cost of movement. Even behaviors that seem passive are carefully tuned strategies for survival. Marine ecologists frequently note that deep-sea ecosystems reward restraint. The animals that last are those that waste the least, not those that move the most. Reproduction in the deep sea often occurs infrequently, but with high investment per offspring, reflecting the high stakes of survival in a food-poor environment. Producing large numbers of offspring requires energy that many deep-sea species simply cannot spare. Instead, reproduction may be delayed for years or even decades, timed to rare favorable conditions. When offspring are produced, they are often larger, better provisioned, or more developed than those of surface species. This increases the chances that at least some will survive the long journey through dark, cold water to suitable habitat. In some cases, parents invest heavily in protecting eggs, or young, a strategy that contrasts sharply with the scatter and hope approach common in surface waters. Biologists studying deep-sea reproduction emphasize that this slow, deliberate strategy mirrors the broader rhythm of life at depth. Reproduction is not frequent, but it is careful, measured, and costly. The slow pace of life in the deep ocean reflects an environment where energy is precious and time is abundant. Growth stretches across decades, lifespans extend far beyond human expectations, and success depends on efficiency rather than urgency. Food scarcity encourages restraint, while reproduction becomes an investment rather than a gamble. In this world, speed offers little advantage. Survival belongs to those that can serve, endure, and wait, moving through life at a pace set not by competition but by patience. Most deep-sea ecosystems depend on organic matter sinking from surface waters, creating a quiet but unbreakable connection between sunlight and darkness. In the upper layers of the ocean, microscopic plants grow using sunlight, multiplying rapidly and forming the base of surface food webs. Fish feed on them, larger animals feed on the fish, and energy moves quickly through this bright, active world. Yet only a small fraction of that energy remains near the surface. When plankton die, when animals produce waste, or when larger creatures perish, gravity takes over. Particles begin drifting downward, carrying stored chemical energy into the depths. By the time this material reaches the deep sea, it has been altered and diminished, but it is still essential. Without this steady downward transfer, most deep-sea life would simply starve. Marine scientists often describe the deep ocean as living on delayed sunlight, surviving on what the surface world sheds. This dependency means that events far above, such as plankton blooms or shifts in climate, can quietly influence life thousands of meters below, long after the surface has moved on. This slow, continuous descent of organic material is known as marine snow, a term that captures both its appearance and its importance. Illuminated by submersible lights, marine snow looks like a gentle snowfall drifting endlessly through black water. Countless tiny particles fall past, moving at different speeds depending on their size and shape. Some sink steadily, others tumble, spiral, or pause, briefly as currents carry them sideways. The journey from surface to seafloor can take weeks or even months, turning the entire water column into a long corridor of falling nourishment. During this descent, marine snow becomes a living habitat of its own. Bacteria and other microorganisms quickly colonize each particle, feeding on it and changing its composition as it sinks. Oceanographers studying the movement of carbon through the ocean have shown that this process plays a major role in transferring carbon away from the atmosphere and into the deep sea. What appears delicate and slow is, over time, one of the most powerful biological processes on the planet. Marine snow is not a single substance, but a constantly changing mixture that reflects the life and activity of the surface ocean. It includes dead plankton, fragments of algae, discarded shells, mucus, fecal pellets, and pieces of larger organisms broken apart during descent. Even material produced near coastlines can eventually drift far offshore and sink into the deep ocean. Each particle carries a different nutritional value, making marine snow an unpredictable food source. Some fragments are rich in energy, while others offer little more than trace nutrients. Deep-sea organisms have adapted to this uncertainty by developing ways to capture and consume whatever arrives. Some use feathery appendages to trap particles from the water, while others graze directly on the seafloor where marine snow accumulates. Microbes play a central role, breaking down complex material into simpler forms that other organisms can use. Scientists often describe marine snow as a moving buffet, sparse and inconsistent, but vital to sustaining life in the deep. Because food arrives slowly and irregularly, scarcity drives opportunistic feeding strategies throughout the deep ocean. There is no predictable schedule for meals, and no guarantee of quality when they do arrive. Many deep-sea animals are not specialists but generalists, capable of consuming a wide range of materials. Some remain motionless for long periods, conserving energy until food drifts close enough to capture. Others move slowly across the seafloor, sampling sediments for any trace of organic matter. Scavengers play a particularly important role, detecting large food falls such as dead fish or marine mammals from great distances. These events trigger brief bursts of activity as animals gather to consume as much as possible before the resource is exhausted. Marine ecologists often note that in the deep sea, success depends less on strength or speed and more on flexibility. When food is rare, the ability to eat almost anything becomes one of the most valuable survival traits. Entire food webs in the deep sea are built around sporadic meals rather than continuous supply, giving these ecosystems a distinct rhythm. Instead of constant feeding, long periods of waiting are punctuated by brief moments of abundance. A single large carcass sinking to the seafloor can support a community for months or even years, attracting scavengers first, then predators, and finally organisms that feed on the remains. Smaller inputs such as marine snow provide a background level of nourishment that sustains slower growing species between major events. This structure creates food webs stretched out over time, where energy moves slowly and efficiently rather than rapidly and wastefully. Scientists studying deep-sea ecology often compare these systems to deserts, where life persists by enduring scarcity rather than exploiting abundance. In the deep ocean, meals are not expected, they are awaited. This reliance on food from above shapes every aspect of deep-sea life. Energy arrives late, altered, and in limited amounts, yet it is enough to sustain vast ecosystems built on patience and efficiency. Marine snow links surface productivity to abyssal survival, while opportunistic feeding strategies allow organisms to endure long gaps between meals. Food webs form around rare events rather than constant flow, creating a world where waiting is as important as feeding. In the deep ocean, nourishment falls slowly through darkness, and life has learned to survive on what eventually arrives. Some deep-sea ecosystems are entirely independent of surface photosynthesis, breaking one of the most familiar assumptions about how life on Earth works. At the surface, nearly all ecosystems trace their energy back to sunlight, captured by plants or microscopic algae and passed along food webs. In the deep ocean, that link usually remains, delayed and weakened as organic material sinks from above. But in certain places, life cuts that cord completely. These ecosystems do not rely on falling debris or surface productivity at all. Instead, they are powered by energy rising from within the Earth itself. This discovery, first confirmed in the late 1970s, reshaped biology and planetary science alike. It demonstrated that sunlight, while dominant, is not the only foundation for complex life. In these dark environments, life thrives without ever receiving a single photon from the sun. The deep ocean becomes not a dependent shadow of the surface, but an independent realm where biology taps into the planet's internal chemistry. For scientists, this was more than a curiosity. It expanded the definition of habitability and suggested that life could exist in places once thought entirely barren. In these sunless regions, chemical energy replaces solar energy, most dramatically at hydrothermal vents scattered along tectonic boundaries. Here, seawater seeps into cracks in the seafloor, heats up as it approaches molten rock, and then erupts back into the ocean, carrying dissolved minerals and chemicals. The water emerging from vents can be hot enough to melt lead, yet it mixes rapidly with near-freezing seawater, creating steep gradients of temperature and chemistry. Instead of light, the primary energy source is chemical imbalance. Compounds such as hydrogen sulfide, which would be toxic to most surface life, become valuable fuel. The vent environment is harsh, unstable, and highly localized, yet it supports dense and thriving communities. Biologists often note the contrast: barren seafloor just meters away, and bustling life clustered tightly around vent openings. This energy is not gentle or evenly distributed. It arrives in pulses, shaped by geological activity, reminding researchers that life here is closely tied to the restless interior of the planet, rather than the steady rhythm of the sun. Microbes sit at the center of this system, converting chemical compounds into usable energy through a process known as chemosynthesis. Instead of using sunlight to drive reactions, these microorganisms use the energy released when certain chemicals react with oxygen or other compounds. Hydrogen sulfide is a common fuel, but methane and hydrogen can also serve as energy sources. Through chemosynthesis, microbes build organic molecules from carbon dioxide, forming the base of an entirely separate food web. This process operates continuously as long as chemical supplies persist, making it resilient to the absence of light. Scientists studying these microbes often emphasize how finely tuned they are to their environment. Enzymes are adapted to function under extreme pressure, high temperatures, and fluctuating chemical conditions. Some microbes live freely in vent fluids, while others form dense mats coating rocks and sediments. In these systems, microbes play the same foundational role that plants and algae play at the surface, quietly powering everything else without drawing attention to themselves. These chemosynthetic microbes form the foundation of unique vent communities, supporting animals that look unlike anything found elsewhere in the ocean. Giant tube worms, clams, mussels, and shrimp gather in dense clusters around vents, often living in close partnership with the microbes themselves. Some animals host bacteria inside their tissues, providing them with chemicals while receiving nutrition in return. Others graze directly on microbial mats, or capture free-living microbes from the water. This tight coupling creates ecosystems that are compact, productive, and sharply defined. Life flourishes where chemical energy is strongest and fades rapidly beyond that zone. Biologists often describe vent communities as islands of abundance surrounded by deep sea scarcity. Their dynamic systems, appearing and disappearing as vents open and close over time. Despite their instability, they demonstrate how quickly life can organize itself when energy is available, even in total darkness. These communities challenge surface-based intuition, showing that sunlight is not a requirement for complexity, cooperation, or ecological richness. Life without sunlight reshapes how the deep ocean is understood. Some ecosystems operate entirely beyond the reach of the sun, powered instead by chemistry and geology. Energy flows upward from the earth rather than downward from the sky, supporting microbes that form the base of dense, specialized communities. These systems reveal a version of life that is self-contained, resilient, and remarkably inventive. In the deep sea, Darkness does not signal absence. It marks a boundary beyond which life follows different rules, drawing power from the planet itself and reminding science that habitability is broader, stranger, and more flexible than once believed. Hydrothermal vents form where seawater interacts with hot rock beneath the seafloor, creating one of the most direct links between the ocean and Earth's interior. Along mid-ocean ridges and volcanic regions, fractures open in the crust, allowing cold seawater to percolate downward through layers of rock. As this water sinks, it is heated by underlying magma and reacts with surrounding minerals, dissolving metals and absorbing gases. Pressure increases with depth, preventing the water from boiling despite rising temperatures. Eventually, the fluid becomes buoyant and is forced back upward, emerging through the seafloor as a hydrothermal vent. This circulation can continue for years or centuries, driven entirely by geological heat rather than surface conditions. Geologists often describe these systems as vast hidden plumbing networks, constantly reshaped by tectonic motion. The process transfers energy from deep within the planet into the ocean, transforming cold seawater into a chemically rich fluid capable of sustaining life in total darkness. In this way, hydrothermal vents reveal how closely linked the deep ocean is to Earth's restless interior, even in places far removed from sunlight and weather. Vent fluids can exceed temperatures hot enough to melt lead, a detail that seems almost unbelievable when paired with the near-freezing seawater that surrounds them. Direct measurements taken at vent openings have recorded temperatures of several hundred degrees Celsius. These fluids remain liquid only because the immense pressure of the deep ocean raises the boiling point of water far beyond everyday experience. As superheated fluid jets into the surrounding cold seawater, dramatic temperature gradients form over distances measured in centimeters. Life cannot survive inside the hottest flows, but thrives at their margins, where hot chemical-rich fluid mixes with cold oxygenated seawater. Marine scientists often note that these boundary zones are among the most extreme yet precisely balanced habitats on Earth. Organisms living there exist in a narrow window between lethal heat and insufficient energy. The presence of such intense heat deep underwater serves as a reminder that the seafloor is not a static landscape, but an active interface between geology and biology, constantly reshaped by forces originating far below the surface. As vent fluids meet cold seawater, minerals precipitate rapidly, building the chimney-like structures that have become iconic symbols of hydrothermal vents. Dissolved metals carried upward in hot fluids cool, almost instantly upon contact with near-freezing seawater. Iron, copper, zinc, and sulfur compounds solidify into fine particles that form clouds before settling and accumulating. Over time, these particles fuse into solid spires that can grow several meters tall. Different chemical compositions produce different appearances, from dark, smoky plumes rich in metal sulfides to lighter-coloured structures dominated by other minerals. These chimneys are not permanent monuments. They grow, crack, collapse, and reform as fluid flow shifts. Geochemists study these mineral layers as records of changing conditions below the seafloor, reading them much like geological diaries. For living organisms, the chimneys provide rare hard surfaces in an otherwise soft sediment environment, creating anchor points for dense biological communities to assemble. Giant tube worms rely on internal bacteria for nutrition, forming one of the most remarkable biological partnerships known from the deep sea. These worms possess no mouths, no stomachs, and no digestive tracts. Instead, they host dense populations of chemosynthetic bacteria within a specialized internal organ. The worm absorbs chemicals such as hydrogen sulfide from vent fluids and oxygen from seawater, delivering both to its bacterial partners. In return, the bacteria convert these chemicals into organic compounds that nourish the worm. This arrangement allows tube worms to grow surprisingly large and relatively quickly compared to many other deep-sea species. Some individuals reach lengths of several feet, forming dense clusters around vent openings. Biologists often describe this relationship as an elegant solution to life in darkness. Rather than searching for food, the worm becomes a living habitat for energy-producing microbes, turning toxic chemicals into sustenance through cooperation rather than competition. Vent fields can appear and vanish over geological timescales, making them both productive and temporary features of the deep ocean. Tectonic shifts can open new pathways for fluid flow or seal existing ones without warning. Some vent systems remain active for decades, while others persist for centuries before cooling and shutting down. When vents cease, the communities built around them often collapse, forcing organisms to disperse or perish. New vents may form nearby, restarting the cycle in a different location. Scientists studying vent species emphasize that this instability has shaped their evolution. Many organisms produce larvae capable of drifting long distances, increasing the chance of colonizing newly formed vents. Life at vents is therefore adapted not only to extreme chemistry and temperature, but to impermanence itself. Survival depends on flexibility and dispersal, rather than long-term stability. Hydrothermal vents reveal a deep ocean shaped by heat, chemistry, and constant geological motion. Seawater circulates through hot rock, emerges transformed, builds mineral structures, and supports dense biological communities through microbial partnerships. These systems demonstrate that life can flourish without sunlight, drawing energy instead from Earth's internal heat. Though individual vent fields may be short-lived on geological timescales, their existence reshapes understanding of where life can thrive, showing that even in darkness and extreme conditions, biology finds a way to endure. Cold seeps release hydrocarbons rather than heat, creating a deep-sea environment that feels calm on the surface but chemically rich beneath. Unlike hydrothermal vents, cold seeps are not driven by magma or intense temperatures. Instead, they occur where hydrocarbons such as methane and hydrogen sulfide slowly leak from sediments below the seafloor. These fluids are often close to the surrounding water temperature, which is why the term cold seep is used. The energy here comes not from heat, but from chemical imbalance. As hydrocarbons escape upward, they provide a steady source of fuel for microorganisms capable of using them. Geologists studying cold seeps often describe them as slow breathing points in the seabed, releasing gases that have been trapped for thousands or even millions of years. The release can be gentle and continuous, or episodic depending on pressure and sediment movement. To an observer, the surrounding seafloor may appear unremarkable, yet beneath it lies a quiet flow of chemical energy that supports life entirely independent of sunlight or surface food fall. Methane-based ecosystems support distinct biological communities that differ noticeably from those found around vents or in surrounding deep-sea regions. Methane becomes the central energy source, shaping which organisms can survive and how they interact. Thick microbial mats often blanket seep areas, forming pale, patchy carpets across the sediment. These microbes consume methane and other hydrocarbons, converting them into biological material that feeds larger organisms. Clams, mussels, worms, and crustaceans gather in dense clusters, taking advantage of this localized productivity. Marine biologists have observed that seep communities tend to be less explosive and more orderly than vent communities, reflecting the steadier energy supply. There are fewer dramatic temperature gradients and less physical instability. Instead, life arranges itself around chemical availability, creating ecosystems that feel slow, persistent, and quietly productive. These communities stand out sharply against the surrounding seafloor, which may host far fewer organisms just a short distance away, highlighting how powerful chemical energy can be even in the absence of heat or light. Some organisms living at cold seeps host methane processing microbes within their tissues, forming intimate partnerships that mirror those seen at hydrothermal vents. Certain clams and mussels lack the ability to feed in conventional ways, relying instead on internal bacteria to meet their nutritional needs. These microbes live inside specialized cells, where they convert methane or methane-derived compounds into organic material. The host organism supplies the microbes with access to hydrocarbons and oxygen, while receiving nourishment in return. This relationship allows animals to thrive in environments where traditional food sources are scarce. Biologists studying these partnerships often note how tightly integrated they are. The physiology of the host is shaped around supporting microbial life, blurring the boundary between individual and ecosystem. This arrangement reduces the need for constant feeding and allows organisms to remain anchored in chemically rich areas for long periods. In the deep sea, cooperation between microbes and animals becomes one of the most reliable strategies for survival. Cold seeps can persist for thousands of years, making them among the most stable chemically driven ecosystems in the deep ocean. Unlike hydrothermal vents, which can appear and disappear as tectonic conditions change, cold seeps often release hydrocarbons at a slow, steady pace over extremely long timescales. This persistence allows biological communities to develop gradually and remain in place for generations. Sediments around long-lived seeps can accumulate thick layers of carbonate minerals formed as a byproduct of microbial activity, creating hardened seafloor features that mark seep locations long after active flow has diminished. Marine scientists studying seep longevity often emphasize how rare such stability is in the deep sea. In an environment shaped by scarcity and unpredictability, cold seeps offer a dependable source of energy. This long-term consistency supports slower growing organisms and more established ecological relationships, reinforcing a style of life built on endurance rather than rapid change. Cold seeps and methane worlds reveal a version of the deep ocean where chemistry unfolds slowly and patiently. Hydrocarbons rise instead of heat, microbes feed instead of plants, and life settles into steady patterns that can last for millennia. These ecosystems demonstrate that energy does not need to arrive violently to be transformative. In the quiet release of methane and the slow work of microbes, the deep sea shows another way life can persist, drawing power from the earth itself and turning stillness into survival. Many deep-sea animals produce their own light, transforming permanent darkness into a world filled with brief flashes, glows, and pulses. In the absence of sunlight, bioluminescence becomes one of the most common biological traits in the deep ocean. Scientists estimate that a majority of midwater and deep-sea species are capable of producing light in some form. This light is created through chemical reactions inside the body, typically involving a light-producing molecule and an enzyme that triggers its glow. The reaction releases energy directly as light rather than heat, making it efficient and well-suited to cold environments. Bioluminescence appears across a wide range of organisms, from tiny plankton to fish, squid, jellyfish, and crustaceans. In the beam of a submersible, the deep sea often looks less empty than expected, with sparks and glimmers appearing suddenly and vanishing just as quickly. For animals living in total darkness, producing light is not a novelty. It is a fundamental tool, as essential as vision or movement, woven deeply into how life survives in the deep ocean. Bioluminescence is used for camouflage, communication, and hunting, serving very different purposes depending on the species and situation. Some animals emit light to startle predators or confuse them during an escape, creating a sudden distraction in the darkness. Others use light as a signal, flashing in specific patterns to attract mates or warn rivals. In hunting, bioluminescence can become a lure. Certain fish carry glowing appendages that draw curious prey close enough to capture. Squid and shrimp may release clouds of glowing fluid, creating decoys that divert attention away from their actual bodies. Marine biologists often point out that in the deep sea, light functions as a language rather than simple illumination. A flash may carry meaning, intent, or threat. Because light travels farther than sound or scent in clear deep water, bioluminescence becomes one of the most efficient ways to interact with other organisms across distance, even in an environment that seems overwhelmingly empty. Counter-illumination helps many deep-sea animals blend into faint surface light, turning bioluminescence into a form of camouflage rather than display. At certain depths, a small amount of dim light filters down from above, creating silhouettes when animals are viewed from below. Predators often scan upward, searching for dark shapes against this faint glow. To avoid being seen, some species produce light on their undersides that matches the brightness and color of the light from above. This erases their shadow, making them nearly invisible from below. The effect is subtle and precise. Too much light would give the animal away, while too little would leave a visible outline. Researchers studying counter-illumination have found that some species can adjust their light output in real time, responding to changes in ambient brightness. In a place where hiding can mean survival, glowing softly becomes a way to disappear rather than stand out, a counterintuitive but highly effective strategy. Light organs vary widely in shape and placement, reflecting the many different ways bioluminescence is used across species. Some animals concentrate light in small, focused organs, while others spread it across large areas of their bodies. Light-producing cells may appear along the belly, near the eyes, at the tips of arms, or in long trailing filaments. In some cases, light organs are paired with lenses, reflectors, or shutters that shape and direct the glow. Fish may have rows of small lights arranged like constellations along their sides, while jellyfish and siphonophores can produce waves of light that travel across their bodies. Biologists often describe deep-sea animals as walking collections of lighting equipment, each design tuned to a specific purpose. The diversity of light organs suggests that bioluminescence has evolved repeatedly and creatively, shaped by different pressures and opportunities. In the deep ocean, light is not a single solution, but a toolkit used in countless ways. Some species can control brightness and timing with remarkable precision, turning light on and off in carefully measured bursts. This control allows animals to flash briefly rather than glow continuously, conserving energy and reducing unwanted attention. Certain fish produce rhythmic patterns, while others emit single, sharp flashes only when needed. Squid can modulate the intensity of their light, dimming or brightening to match surrounding conditions. Scientists studying these behaviors have found that bioluminescent signals are often tightly linked to nervous system control. allowing rapid responses to threats or opportunities. In some species, light production is synchronized across groups, creating coordinated displays that may confuse predators or facilitate communication. The ability to fine-tune light output reflects how valuable bioluminescence is in the deep sea. It is not wasted or casual. It is used deliberately, sparingly, and with purpose, underscoring its importance as a survival tool rather than decoration. Bioluminescence turns the deep ocean from a place of absolute darkness into a landscape of fleeting signals. Light is produced by life itself, shaped into tools for hiding, hunting, and communication. From subtle camouflage to dramatic flashes, these brief moments of illumination define how many deep-sea animals interact with their world. In an environment without sunrise or sunset, bioluminescence becomes the primary way life announces its presence, conceals its shape, and navigates a realm where light exists only when living organisms choose to create it. Deep-sea animals often appear exaggerated or unfamiliar to surface observers because their bodies have been shaped by conditions that feel almost unreal from a human perspective. When cameras first returned images of deep-sea creatures, scientists themselves were often startled by what they saw. Elongated limbs, oversized heads, tiny eyes, or eyes that dominate the entire face can give these animals an almost surreal appearance. This is not because deep sea life is poorly designed, but because it is designed for a world without light, warmth, or abundance. In the deep ocean, there is little reason to resemble surface animals, whose forms are shaped by gravity, sunlight, and constant motion. Instead, body shapes reflect the need to sense faint signals, conserve energy, and survive long periods without food. What looks grotesque or exaggerated to surface observers is often the most efficient possible solution to a specific problem. Marine biologists frequently emphasize that deep-sea animals only seem strange because they evolved under rules humans rarely encounter. Their forms are not extreme by accident. They are precise responses to an extreme environment. Large mouths and expandable stomachs allow rare meals to be maximized, turning unpredictability into opportunity. In the deep ocean, food does not arrive on a schedule. When it does appear, it may be small and fleeting, or it may be unexpectedly large. Many deep-sea fish have evolved mouths that appear absurdly oversized compared to their bodies, lined with long inward-pointing teeth. These mouths allow them to capture prey nearly as large as themselves, something that would be impractical or impossible for surface species. Expandable stomachs and flexible body walls then allow the animal to store and digest this meal slowly over time. This strategy reflects a simple truth of deep-sea life. Passing up food is dangerous, because the next opportunity may be weeks or months away. Scientists studying deep-sea feeding behavior often note that these animals are built not for frequent meals but for rare windfalls. A single successful capture can sustain an animal for a long time. In this environment, the ability to eat big matters far more than the ability to eat often. Transparent bodies reduce visibility in faint light, offering a subtle but powerful form of camouflage. At certain depths, darkness is not absolute. A dim glow from above may still penetrate, and bioluminescent flashes can briefly illuminate the water. In such conditions, being opaque can make an animal visible from surprising distances. Transparency solves this problem by allowing light to pass through the body rather than reflect off it. Many deep-sea animals, including jellyfish, shrimp, and some fish, are partially or almost entirely transparent. Organs may be minimized, rearranged, or hidden to reduce contrast. Blood may be colourless rather than red, and tissues may lack pigmentation altogether. To the human eye, these animals can look ghostly or unfinished, but their design is highly effective. Marine researchers often point out that transparency is one of the few ways to become nearly invisible in a world where hiding places are scarce. In the deep sea, the best camouflage is sometimes to have no visible outline at all. Fragile tissues conserve energy in the calm, low-motion environment of the deep ocean, where strength is often unnecessary. Near the surface, animals must contend with waves, currents, and constant movement. Muscles, rigid skeletons, and dense tissues help resist these forces. In the deep sea, water movement is minimal. Currents are slow, and storms at the surface rarely disturb the depths. Under these conditions, heavy muscles and thick bones become costly rather than useful. Many deep-sea animals have soft, gelatinous bodies with low muscle mass and reduced skeletal structures. This fragility would be disastrous in shallow water, but at depth it offers significant advantages. Soft tissues require less energy to maintain, allowing animals to survive on limited food supplies. Buoyancy is easier to control, and slow drifting replaces active swimming. Biologists often describe deep-sea animals as energy minimalists, built to exist rather than to exert. Their apparent delicacy is not weakness, but efficiency shaped by an environment that rewards stillness over strength. These extreme body forms reflect a world where survival depends on efficiency, patience, and adaptation, rather than power or speed. Exaggerated shapes help animals sense scarce signals. Oversized mouths ensure that rare meals are never wasted. Transparency erases outlines in faint light, and fragile tissues reduce energy demands in a calm environment. Together, these traits reveal a deep ocean where form follows function with remarkable honesty. What appears strange or unsettling to surface observers is, in reality, a collection of elegant solutions to life under pressure, darkness, and scarcity. Some deep-sea species grow unusually large compared to their shallow water relatives, a pattern that has intrigued scientists for over a century. This phenomenon, often called deep-sea gigantism, can be seen in creatures such as giant isopods, amphipods, and squid that far exceed the size of similar species living closer to the surface. What makes this especially striking is that these animals are not living in environments rich in food or warmth, conditions usually associated with large body size. Instead, they inhabit cold, dark waters where resources are scarce. Marine biologists suggest several explanations. A larger body can store more energy, allowing an animal to survive long periods without food. Size can also reduce the number of potential predators, since fewer species are capable of attacking very large prey in the deep ocean. In some cases, larger size may improve efficiency, as bigger bodies lose heat more slowly and can move with less relative energy cost. To surface observers, these animals can look monstrous or out of proportion, but in the deep sea, being big can be a sensible response to an environment where opportunities are rare and endurance matters more than speed. Cold temperatures play a key role in this pattern by slowing metabolism, enabling extended growth over long periods of time. In warm environments, chemical reactions in the body proceed quickly, leading to faster growth, but also faster aging and higher energy demands. In the deep ocean, near freezing temperatures slow these reactions dramatically. Growth still occurs, but at a reduced pace, stretched out over decades rather than years. This slow biological clock allows some organisms to continue growing for much of their lives instead of reaching a fixed adult size early on. Marine scientists studying growth patterns in deep-sea animals often find that age and size are closely linked, with older individuals simply having had more time to accumulate tissue. Slow metabolism also reduces the overall cost of being large. Energy is spent carefully, and maintenance demands are lower than they would be in warmer water. In this way, cold does not just limit life, it reshapes it, allowing bodies to grow gradually and persist for long spans of time in an environment that rewards patience. While some species grow large, other deep-sea organisms remain extremely small, using miniaturization as an equally effective survival strategy. Tiny body size reduces energy demands, which is a critical advantage in a place where food is unpredictable and often scarce. Small organisms require less nourishment to survive and can exploit resources that larger animals cannot, such as microscopic particles within sediments or thin films of organic material coating rocks. Many deep-sea worms, crustaceans, and microorganisms exist at scales that make them nearly invisible to the human eye, yet they are abundant and ecologically important. For these species, being small also allows rapid reproduction when conditions permit, spreading risk across many offspring. Marine ecologists often note that the deep sea does not favor a single ideal size. Instead, it supports a wide range of body plans, each tuned to different ways of accessing limited energy. In this environment, shrinking down can be just as advantageous as growing large, depending on how an organism feeds and lives. These extremes of size reflect careful trade-offs between feeding and survival, rather than random variation. Large bodies offer advantages in storage, defense, and efficiency, but they come with higher initial costs and longer development times. Small bodies reduce energy needs and allow flexibility, but they can limit access to certain food sources and make organisms vulnerable to being overlooked rather than protected. In the deep ocean, evolution does not push life toward an average. It pushes it towards solutions that work under pressure, cold, and scarcity. Scientists studying deep-sea ecosystems often emphasize that these size extremes coexist because they occupy different roles within the same environment. Together, they form a balanced system where both giants and tiny specialists can persist. Gigantism and miniaturization reveal the deep ocean as a place where size is shaped less by abundance and more by strategy. Cold temperatures slow time, allowing some organisms to grow steadily across decades, while others conserve energy by remaining small and efficient. These contrasting approaches highlight how life adapts to extremes, not by converging on a single form, but by exploring the full range of what is physically and biologically possible. Sound travels farther in deep water than in air, making the ocean a surprisingly connected acoustic environment despite its darkness. Water is far denser than air, and this density allows sound waves to move faster and lose less energy as they travel. In the deep ocean, low-frequency sounds can propagate for hundreds or even thousands of kilometers, bending and refracting through layers of water with different temperatures and pressures. Oceanographers have identified natural sound channels where noise becomes trapped and carried vast distances with little loss. This means that a sound produced in one part of the ocean can be detected far away, long after its source has faded from view. In a place where light is absent and vision is limited, sound becomes a dominant way information moves through the environment. The deep sea is not silent in the way empty space is silent. It is filled with distant echoes, subtle vibrations, and low background hums that link remote regions together into a single acoustic world. Because of this, many deep-sea animals rely on detecting vibrations rather than light to sense their surroundings. Eyes may be reduced, absent or secondary, while sensory systems tuned to movement and pressure changes become highly developed. Fish, crustaceans and invertebrates often possess sensitive lateral line systems or similar structures that allow them to detect minute disturbances in the water. These systems can reveal the presence of nearby animals, shifting currents, or approaching predators without requiring direct contact or illumination. Some species can even determine the direction and distance of a disturbance based on how vibrations reach different parts of their bodies. Marine biologists studying deep-sea sensory biology often emphasize that these animals experience their world as a field of motion rather than a visual landscape. In darkness, vibration becomes a reliable signal. It carries information continuously and does not depend on producing light that might also attract attention. For many deep-sea species, feeling the ocean is more important than seeing it. Natural sounds in the deep ocean come from a wide range of sources, creating an ever-changing acoustic background. Earthquakes send low-frequency waves through the seafloor and water column, sometimes audible across entire ocean basins. Ice cracking and a shifting in polar regions produces sharp, resonant sounds that travel far beneath the surface. Marine animals contribute as well. Whales call across vast distances, fish produce grunts, clicks, and hums, and invertebrates generate subtle noises through movement and feeding. Even the slow movement of currents over seafloor features can create faint but persistent sounds. Scientists who deploy deep-sea listening equipment often describe the experience as hearing a hidden side of the planet. The ocean reveals its activity not through light or colour, but through rhythm and vibration. These natural sounds provide cues about distant events, allowing both animals and researchers to sense changes occurring far beyond their immediate surroundings. Human noise now penetrates even remote deep-sea regions, altering this ancient soundscape in ways that are only beginning to be understood. Ship engines, seismic surveys, construction, and resource exploration generate powerful low-frequency sounds that travel efficiently through water. Unlike many natural noises, these sounds can be continuous, repetitive, and intense. Studies have shown that human-generated noise can overlap with the frequencies used by marine animals for communication and navigation. In the deep sea, where sound travels so effectively, noise from surface activity can reach habitats once considered isolated. Marine scientists are increasingly concerned that this acoustic pollution may interfere with feeding, mating, and movement patterns, even at great depths. Unlike visible disturbances, sound leaves no obvious trace, making its impact harder to measure. Yet for animals that rely on vibration as their primary sense, changes to the acoustic environment can be profound. The deep ocean, long shaped by natural rhythms, is now beginning to carry the echoes of human activity as well. Sound and silence in the deep sea exist in a delicate balance. Water carries vibrations farther than air ever could, turning the ocean into a vast medium for communication and awareness. Deep-sea animals listen and feel more than they see, navigating a world defined by motion rather than light. Natural sounds from geology, ice, and living creatures have filled this space for millions of years, creating a complex and meaningful background. Today, human noise is becoming part of that environment, reaching into depths once untouched. The deep ocean may appear silent from the surface, but beneath the waves it is alive with sound, shaping how life senses, survives, and responds to a changing world. The deep sea floor includes plains, mountains, trenches, and volcanoes, forming a landscape as varied and dramatic as anything found on land. Hidden beneath kilometers of water, this terrain was once imagined as flat and featureless. But modern mapping has revealed a world shaped by powerful geological forces. Vast mountain ranges run across the ocean floor, some longer than continental chains on land. Volcanoes rise from the seabed, many still active, quietly building new crust. Trenches plunge downward where tectonic plates bend and descend, creating the deepest places on the planet. There are cliffs, escarpments, plateaus, and fracture zones, all sculpted by slow movement and immense pressure. Geologists often note that the seafloor records Earth's internal activity more clearly than the continents do, because erosion by wind and rain plays almost no role. Everything is shaped from below rather than above. Although these features are largely invisible from the surface, they dominate the physical structure of the planet, reminding scientists that Earth's most extensive landscapes lie out of sight, evolving steadily beneath the ocean. Abyssal plains are among the flattest places on Earth, stretching across enormous areas of the deep ocean with remarkable uniformity. These plains lie thousands of meters below the surface, far from continents and major geological boundaries. Over millions of years, fine sediments settle slowly onto these regions, filling in low spots and smoothing out irregularities. The result is a seafloor that can be flatter than many deserts or plains on land. Oceanographers mapping these areas often describe them as vast, dark expanses where the horizon feels almost endless. Despite their apparent emptiness, abyssal plains are not lifeless. They host communities adapted to sparse food and stable conditions, living on a surface that changes at a glacial pace. The flatness itself influences how water moves near the bottom and how nutrients are distributed. In a world defined by extremes elsewhere, abyssal plains represent quiet stability, shaped not by violence but by patience and time. Deep-sea trenches mark zones where tectonic plates collide, creating the deepest scars on Earth's surface. These trenches form where one plate is forced beneath another, bending downward into the mantle in a process known as subduction. The resulting features can extend for thousands of kilometers and reach depths greater than any mountain is tall. Conditions in trenches are extreme even by deep-sea standards, with crushing pressure, near freezing temperatures, and limited food supply. Yet life persists, adapted to conditions once thought uninhabitable. Scientists exploring trench environments have discovered unique organisms capable of surviving pressures that would instantly destroy surface life. These regions also play a critical role in Earth's geological cycle, recycling crust back into the interior and driving volcanic activity elsewhere. Trenches are not just deep holes. They are active boundaries where the surface of the planet is continuously reshaped from below. Sediments accumulate extremely slowly on the deep seafloor, building up layer by layer over millions of years. In many deep ocean regions, only a few millimeters of sediment may settle over 1,000 years. This slow pace means that the seafloor acts as a long-term archive of Earth's history. Tiny shells, mineral particles and organic fragments fall from above and settle gently, preserving records of past climates, ocean chemistry and biological activity. Oceanographers studying sediment cores can read these layers like pages in a book, tracing changes that span tens of millions of years. Because disturbances are rare, older layers remain largely undisturbed, unlike sediments on land that are constantly reworked by weather and erosion. The deep sea floor therefore preserves a more continuous record of planetary history than most environments on Earth. Time moves slowly here, and the ground itself becomes a memory of the planet's past. Tracks and burrows etched into the seafloor reveal hidden animal activity in a place that often appears still and empty. Even where animals are rarely seen, their movements leave subtle marks in soft sediments. Winding trails show where organisms have crawled in search of food. Burrows indicate hidden lives beneath the surface, where animals feed, rest, and avoid predators. These traces can persist for long periods because currents are weak and disturbances are minimal. Marine biologists often rely on such signs to understand behavior in environments where direct observation is difficult. A single track can reveal feeding strategies, movement patterns, or interactions between species. In this way, the seafloor becomes a canvas recording the quiet routines of deep sea life. Although the animals themselves may remain out of sight, their presence is written clearly into the sediment, telling stories of survival in an environment defined by scarcity and calm. The deep sea floor is not a uniform abyss, but a complex and dynamic landscape shaped by geology, time, and life. Mountains and trenches reflect the planet's internal motion, while abyssal plains and sediments record patience on a scale difficult to imagine. Even in apparent stillness, subtle signs reveal constant biological activity. Together, these features show that the deep sea floor is both a stage for Earth's most powerful forces and a quiet archive of its long history, changing slowly but never truly at rest. Many deep-sea fish lack swim bladders due to the immense pressure found at depth, a structural choice that reflects physics as much as biology. Near the surface, swim bladders allow fish to control buoyancy by adjusting the volume of gas inside their bodies. This system works well in relatively shallow water, where pressure changes are modest. In the deep ocean, however, pressure increases so dramatically that gas-filled organs become unstable and difficult to regulate. Any rapid change in depth would cause gas to compress or expand dangerously, risking injury or loss of control. As a result, many deep-sea fish abandon swim bladders entirely. Instead, they rely on alternative strategies such as lightweight tissues, reduced bone density, and body compositions that closely match the density of seawater. Some accumulate oils or gelatinous substances that provide passive buoyancy without the risks associated with gas. Marine biologists often point out that this makes deep-sea fish poorly suited to life near the surface, where their bodies may collapse or malfunction. Their anatomy is not incomplete. It is precisely tuned to a world where pressure is constant and unforgiving, and where stability matters more than flexibility. Slow swimming is another defining trait of many deep-sea fish, reflecting the need to conserve energy in environments where food is scarce and unpredictable. In surface waters, speed can mean survival. Fish dart, chase, and flee in a constant race driven by abundant life and competition. In the deep ocean, such behavior would be wasteful. Every movement costs energy, and calories are not easily replaced. As a result, many deep-sea fish move deliberately, drifting or hovering rather than actively swimming for long periods. Muscles may be reduced, and bodies shaped to minimize effort rather than maximize speed. This slow pace does not mean inactivity or vulnerability. Instead, it reflects a careful balance between motion and rest. Fish remain alert, ready to respond when food appears, but they avoid unnecessary exertion. Researchers studying deep-sea behavior often describe these animals as economical rather than sluggish. In a world where meals may be separated by days or weeks, conserving energy becomes the most reliable survival strategy. Some deep-sea fish use lures to attract prey, turning patience into a hunting method. In total darkness, actively searching for food can be inefficient, so many predators let food come to them. The most famous example is the anglerfish, which carries a bioluminescent lure extending from its head. This glowing tip flickers gently in the dark, mimicking the movement of small organisms. Curious prey drawn toward the light often come within striking distance before realizing the danger. Other species use different variations of this approach, producing light from modified fins, barbels, or patches of skin. The lure does not need to be bright or dramatic. Even a faint glow can stand out in complete darkness. Marine biologists often note that this strategy reduces the need for long chases, saving energy while increasing success. In the deep ocean, attracting prey is often more efficient than pursuing it. The lure becomes an extension of the predator's body, a quiet invitation that turns scarcity into opportunity. Reproduction strategies among deep-sea fish vary widely across depth zones, reflecting the challenges of finding mates in a vast, sparsely populated environment. In some species, individuals may rarely encounter one another, making traditional mating strategies impractical. This has led to remarkable adaptations. Certain fish produce large numbers of eggs to increase the chance that some will survive and find suitable conditions. Others invest heavily in fewer offspring, providing them with greater energy reserves. Some species rely on synchronized spawning, releasing eggs and sperm at the same time, in response to environmental cues such as chemical signals or subtle changes in water conditions. In the most extreme cases, such as certain anglerfish, males permanently attach themselves to females, ensuring reproductive success whenever eggs are produced. Marine scientists emphasize that these strategies are not oddities, but logical responses to isolation and low population density. In the deep sea, reproduction is shaped less by competition and more by the challenge of simply finding another individual of the same species. Deep-sea fish reveal how life adapts when pressure is constant, food is limited, and encounters are rare. Bodies are shaped to remain stable without gas-filled organs, movement slows to conserve energy, hunting becomes an exercise in patience, and reproduction follows creative paths shaped by isolation. These fish are not poorly equipped versions of surface species. They are specialists, refined for a world where efficiency matters more than speed, and where survival depends on making the most of every opportunity that appears in the dark. Invertebrates dominate deep-sea ecosystems by number and diversity, forming the true backbone of life at depth. While fish and other vertebrates tend to capture attention, they represent only a small fraction of the organisms living on or above the deep-sea floor. Instead, the vast majority of species belong to groups without backbones, including worms, crustaceans, mollusks, and a wide array of microscopic life. This dominance is not accidental. Invertebrates are exceptionally flexible in their body plans and lifestyles, allowing them to adapt to extreme pressure, low temperatures, and scarce food with remarkable efficiency. Many can survive long periods without feeding, reproduce in unusual ways, or occupy tiny ecological niches that vertebrates cannot exploit. Marine biologists studying deep sea samples often report that a single scoop of sediment can contain dozens or even hundreds of invertebrate species, many of them small, slow-moving, and easily overlooked. When biodiversity is measured by sheer numbers and functional roles, invertebrates overwhelmingly shape how deep-sea ecosystems function, recycle nutrients, and persist over time. Crustaceans, worms, and mollusks fill many ecological roles in the deep ocean, acting as scavengers, predators, filter feeders, grazers, and ecosystem engineers. Crustaceans such as amphipods, isopods, and shrimp range from tiny sediment dwellers to large scavengers capable of rapidly consuming fallen carcasses. Worms burrow through sediments, mixing and oxygenating layers while feeding on organic matter trapped below the surface. Mollusks, including clams, snails and octopuses, occupy roles that span from passive filtering to active hunting. Some species host symbiotic microbes, while others scrape microbial films from rocks or prey on smaller animals. This diversity of feeding strategies allows invertebrates to exploit nearly every available energy source, no matter how limited or unpredictable. Marine ecologists often emphasize that deep-sea food webs are held together by invertebrate activity. Without them, organic matter would accumulate unused, sediments would stagnate, and energy flow would slow dramatically. In the deep ocean, invertebrates are not background players. They are the primary drivers of ecological balance. Soft bodies tolerate pressure better than rigid skeletons, giving many invertebrates a distinct advantage in the deep sea. High pressure compresses gases, fluids, and even solid materials, placing stress on rigid structures. Animals with hard skeletons or gas-filled spaces face greater risks as depth increases. Soft-bodied organisms, by contrast, experience pressure more evenly across their tissues, reducing the likelihood of structural failure. Jellyfish, worms, sea cucumbers, and many mollusks rely on flexible bodies that deform gently rather than resist compression. This makes them well suited to environments where pressure is constant and extreme. Reduced skeletons also lower energy costs, an important consideration in food-poor conditions. Marine biologists frequently note that deep-sea animals often appear delicate or gelatinous, but this softness is a strength rather than a weakness. In calm, deep waters, where currents are slow and physical impacts are rare, rigidity offers little benefit. Flexibility allows invertebrates to survive and function efficiently under conditions that would challenge more heavily built animals. Many deep-sea invertebrate species remain undescribed by science, highlighting how little of this vast ecosystem has been fully explored. Every deep-sea expedition that samples sediments, rocks, or vent communities tends to uncover organisms that do not match known species. Some are entirely new to science, while others belong to poorly understood groups with few formal descriptions. The challenges of deep-sea research contribute to this gap. Sampling is difficult, expensive, and limited in scope, and many organisms are fragile or microscopic, making them hard to collect intact. Invertebrates, with their immense diversity and often subtle differences, are especially challenging to catalogue. Taxonomists working with deep-sea material frequently spend years examining specimens to determine whether they represent new species. Scientists estimate that a significant portion of deep-sea biodiversity remains undocumented, particularly among small invertebrates living within sediments. This means that current knowledge likely captures only a fraction of the true complexity of deep-sea life. Each new discovery adds to the understanding that the deep ocean is not only vast, but biologically rich in ways that are still unfolding. Invertebrate dominance reveals the deep sea as a realm built on flexibility, diversity, and quiet efficiency. Without backbones or rigid forms, these organisms fill nearly every ecological role imaginable, from recycling waste to sustaining food webs. Their soft bodies suit extreme pressure, their varied lifestyles exploit scarce resources, and their sheer numbers underpin ecosystem stability. The fact that so many species remain unknown underscores how much of this world is still waiting to be understood. In the deep ocean, life thrives not through size or strength, but through adaptability and diversity at every scale. Deep-sea corals can live for thousands of years, making them some of the longest-lived animals on the planet. Unlike their shallow water relatives, which often grow quickly and form colourful reefs in sunlit environments, deep-sea corals exist in cold, dark water where growth is extremely slow. Many of these corals do not rely on photosynthesis at all. Instead, they capture tiny particles drifting past in the currents, building their skeletons gradually over centuries. Scientists studying certain species have dated individual corals to ages exceeding several thousand years, meaning they began growing long before recorded human history. A single coral colony may have been alive while civilizations rose and fell above the ocean surface. This extraordinary longevity is made possible by stable conditions, low metabolic rates, and a lack of frequent disturbance. In the deep sea, storms, temperature swings, and seasonal stressors barely register. Life unfolds slowly, and survival depends on endurance rather than speed. These ancient corals are living witnesses to deep time, quietly growing in darkness while the world above changes again and again. As deep-sea corals grow, they form growth rings that record ocean history in a way strikingly similar to tree rings on land. Each layer added to the coral skeleton reflects the chemical conditions of the surrounding seawater at the time it formed. Elements such as carbon, oxygen, and trace metals become locked into the structure, preserving information about temperature, circulation patterns, and nutrient availability. By carefully sampling and analyzing these layers, oceanographers can reconstruct past ocean conditions stretching back thousands of years. This makes deep-sea corals invaluable natural archives, unlike surface records that may be disrupted by erosion or biological activity. Coral skeletons often remain well preserved in the calm depths. Scientists can read periods of warming, cooling, and changes in ocean chemistry with remarkable precision. These growth rings provide insight into long-term climate patterns that cannot be observed directly, helping researchers understand how the ocean has responded to natural changes over deep time. In this way, corals serve not only as living organisms, but as record keepers, quietly storing the ocean's memory layer by layer. Slow biological processes throughout the deep sea reflect an environment defined by stability rather than fluctuation. Near the surface, life is shaped by cycles of day and night, seasons, and shifting weather. In the deep ocean, those cycles fade away. Temperatures remain nearly constant, light never arrives, and physical disturbances are rare. As a result, biological processes slow down. Growth, reproduction, and metabolism unfold at a measured pace. Many deep-sea organisms take years to reach maturity, and some reproduce only infrequently. This slowness is not a disadvantage. In a stable environment, there is little pressure to rush. Marine biologists often note that deep sea life appears almost detached from time as humans experience it. Events that would be dramatic at the surface barely ripple through the depths. The slow pace reduces energy demands and increases longevity, allowing organisms to persist for decades or centuries. Stability shapes not just individual lifespans but entire ecosystems, creating communities that change gradually and resist sudden disruption. The deep sea preserves records of past climates more effectively than almost any other environment on Earth. Fine sediments settle slowly onto the seafloor, accumulating layer by layer over millions of years. These sediments contain microscopic shells, chemical signatures, and organic fragments that reflect conditions at the time they were deposited. Because currents are weak and disturbances are minimal, these layers often remain intact, forming continuous archives of Earth's climatic history. Scientists extract long cores from the seafloor and analyze them to track changes in temperature, ice volume, ocean circulation, and atmospheric composition. The deep sea acts like a vast library, storing information about ancient climates long after surface evidence has vanished. This preservation allows researchers to study how Earth's climate system has behaved over deep time, including periods far warmer or colder than today. In a world where surface environments are constantly reshaped, the deep ocean offers rare continuity, holding on to the planet's past with remarkable fidelity. Longevity and time take on a different meaning in the deep ocean. Corals grow across millennia, biological processes unfold slowly, and the seafloor quietly records Earth's climatic history. Life here is shaped by patience and persistence rather than urgency. The deep sea does not rush to change, and in doing so it becomes both a refuge for ancient life and a record of the planet's long story, written not in words but in layers of growth, chemistry, and stone. Humans reach the deep sea only through specialized technology, because the environment itself is fundamentally hostile to the human body. Crushing pressure, near freezing temperatures, and complete darkness make unprotected access impossible. Even at relatively modest depths, pressure increases to levels that would collapse lungs, rupture blood vessels, and crush bones. To survive, humans must rely entirely on engineered systems that recreate surface conditions inside rigid shells. Submersibles, pressure-resistant housings, and life support systems act as artificial islands of habitability, allowing brief visits into a world that cannot be entered naturally. Ocean engineers often describe deep-sea exploration as less like diving and more like spaceflight, where survival depends on maintaining a controlled internal environment against overwhelming external forces. Every descent requires careful planning, redundancy, and constant monitoring. A single failure can be catastrophic. This reliance on technology means that human presence in the deep sea is always indirect, mediated through machines that stand between fragile biology and an unforgiving environment. Manned dives into the deep ocean remain rare and costly, reflecting both technical challenges and practical limits. Only a small number of submersibles in the world are capable of carrying people to extreme depths, and each dive represents years of design, testing, and maintenance. The cost of building and operating these vehicles is immense, often limiting missions to a handful each year. Time at depth is also constrained. Even when a dive is successful, human occupants may spend only a few hours observing before returning to the surface. Physical endurance, life support capacity, and safety margins all place strict limits on how long people can remain below. As a result, direct human observation of the deep sea is precious and infrequent. Scientists often note that a single manned dive can become historic simply because of how rarely it occurs. While these missions provide unique perspectives and intuitive understanding, they are not scalable. Human eyes in the deep ocean remain the exception rather than the rule. Because of these constraints, remote vehicles now gather most deep-sea observations, quietly expanding human knowledge far beyond what direct presence allows. Remotely operated vehicles and autonomous systems can descend repeatedly, stay underwater for long periods, and reach depths that exceed human-rated limits. These machines carry cameras, sensors, and sampling tools, transmitting data back to researchers on ships or land. Unlike manned submersibles, they do not need life support, rest, or protection from psychological stress. This allows them to explore systematically, mapping large areas, revisiting sites, and operating in conditions too risky for people. Marine scientists increasingly rely on these robotic explorers to study ecosystems, geology, and chemistry at depth. Although they lack the immediacy of human observation, they compensate with persistence and precision. The modern understanding of the deep ocean has been shaped largely by these silent machines, extending human reach into environments that would otherwise remain completely inaccessible. Despite advanced technology, every deep-sea expedition reveals unexpected discoveries, underscoring how incomplete current knowledge remains. New species are encountered regularly. Familiar organisms are observed behaving in unfamiliar ways. Entire ecosystems appear where none were predicted. Instruments detect chemical signals that challenge existing models, and geological features emerge that were previously unmapped. Scientists often remark that even well-studied regions can still surprise, because observation has been so limited. The deep ocean resists neat classification. Each descent feels less like revisiting known territory and more like opening a new chapter. This unpredictability is not a sign of poor science, but of scale. The deep sea is vast, complex, and sparsely sampled. Every expedition adds pieces to a puzzle that remains far from complete, reminding researchers that exploration is still ongoing. Human presence in the deep ocean is brief, mediated, and incomplete. Technology allows entry, but only under strict limits. Manned dives remain rare moments of direct encounter, while robotic explorers quietly gather most of what is known. Yet even with these tools, the deep sea continues to surprise. It remains a place where discovery is the rule rather than the exception, and where human understanding advances slowly, one careful descent at a time. Deep-sea mining targets minerals that formed over millions of years, making the resource itself a product of extraordinary patience. On vast stretches of the abyssal seafloor lie fields of metal-rich nodules, crusts, and sulfide deposits that grow at rates so slow they challenge human intuition. Some nodules increase in size by only a few millimeters over 1 million years, accumulating metals such as manganese, cobalt, nickel, and copper as dissolved elements slowly precipitate from sea water. These materials are attractive to industry because they contain components used in modern technologies, including batteries and electronics. Yet their origin matters. These deposits are not renewable on any meaningful human timescale. Once removed, they are effectively gone forever. Marine geologists emphasize that deep-sea minerals represent a geological archive as much as a resource, recording chemical conditions that existed long before humans appeared. Mining them is not comparable to extracting surface rock. It is the removal of structures that required immense spans of time to form, in environments that change only very slowly. The disturbance caused by deep-sea mining may last longer than human civilization has existed, a possibility that concerns many scientists studying long-term environmental impact. When mining equipment moves across the seafloor, it does not simply remove minerals, it disturbs sediments that may have remained undisturbed for millions of years. Plumes of fine particles can spread far beyond the mined area, settling slowly and potentially smothering organisms over wide regions. Because sediment accumulation in the deep sea is extremely slow, any disruption may persist for thousands or tens of thousands of years. Tracks left by experimental mining tests decades ago are still visible today, with little sign of recovery. Researchers often point out that human history, from the first cities to the present, spans only a few thousand years. In contrast, deep-sea disturbances may outlast entire civilizations, remaining etched into the seafloor long after surface societies have changed beyond recognition. This mismatch between human decision-making timescales and deep-sea recovery timescales lies at the heart of the risk. Ecosystem recovery in the deep sea is extremely slow, reflecting the same conditions that allow life there to endure for centuries. Low temperatures, limited food, and slow biological processes mean that growth and reproduction take a long time. When habitats are damaged, recolonization does not happen quickly. Many deep-sea species grow slowly, reproduce infrequently, and depend on stable conditions. Removing hard substrates such as nodules also removes habitat for organisms that attach to them, including sponges and corals that may take hundreds or thousands of years to reach maturity. Scientists studying experimental disturbance sites have found that even after decades, communities often fail to return to their original state. Some species do not come back at all. This raises difficult questions about what recovery actually means in the deep sea. Is it the return of similar species, the same structure, or the same function? In many cases, full recovery may not be possible within any time frame humans can reasonably observe or manage. Scientific understanding of deep-sea ecosystems often lags behind industrial interest, creating a gap between knowledge and action. While technology has made deep-sea exploration more feasible, large areas remain poorly studied. Many species have not been described, and basic ecological relationships are still being uncovered. At the same time, economic and political pressures push toward resource extraction to meet growing demand for materials. Scientists frequently caution that decisions are being considered faster than understanding can develop. Baseline data are incomplete, long-term studies are rare, and cumulative impacts are difficult to predict. This imbalance places researchers in a reactive position, trying to assess consequences after plans are already underway. Marine science bodies have repeatedly called for caution, emphasizing that the deep sea is not an empty wasteland but a complex and fragile system. Without sufficient knowledge, risk assessment becomes guesswork, and irreversible changes may occur before their full significance is understood. Resources and risk are tightly linked in the deep ocean. Minerals that took millions of years to form are being considered for extraction on human timescales. Disturbance may persist far longer than civilization itself, while ecosystems recover at a pace measured in centuries or millennia. At the same time, scientific understanding struggles to keep up with industrial ambition. The deep sea presents a profound challenge, asking whether short-term gain can be weighed responsibly against impacts that may last longer than history itself. Plastics have been found in the deepest trenches on Earth, overturning the assumption that remoteness offers protection from human impact. Samples collected from some of the deepest parts of the ocean have revealed plastic bags, fibers, and fragments resting on the seafloor thousands of meters below the surface. These materials do not arrive quickly. They drift, sink, fragment, and travel along complex pathways driven by currents and gravity. Over time, even lightweight plastics can descend into trenches, where water movement is slow and removal is unlikely. Scientists studying these environments have expressed surprise not at the presence of plastics, but at how widespread they are. The deepest places on the planet, once thought isolated from surface activity, now carry clear evidence of human waste. Plastics persist because they degrade extremely slowly in cold, dark conditions. Without sunlight or strong mechanical abrasion, breakdown can take centuries or longer. In the deep sea, plastic does not disappear. It accumulates, quietly becoming part of the environment in places that have existed unchanged for millions of years. Chemical pollutants also sink and accumulate over time, following pathways that gradually carry contamination into the deep ocean. substances released at the surface, including heavy metals, pesticides, and industrial chemicals, often bind particles of organic matter. As this material sinks, it transports pollutants downward, embedding them into deep-sea sediments. Unlike surface waters, where dilution and mixing can reduce concentrations, the deep sea acts as a long-term reservoir. Cold temperatures and slow biological activity limit breakdown, allowing chemicals to persist for decades or centuries. Scientists analyzing sediment cores have found clear records of industrial pollution, with layers corresponding to periods of increased chemical use. These records show that even short bursts of surface contamination can leave long-lasting traces at depth. Once pollutants settle into deep sediments, they may be disturbed only rarely, but when they are, they can be reintroduced into the food web. The deep ocean does not flush pollution away, it stores it. Microplastics enter food webs even in the deep ocean, demonstrating how pervasive these materials have become. As larger plastic items break down, they fragment into tiny particles that are easily ingested by organisms. Deep-sea animals consume microplastics directly by mistake or indirectly through contaminated prey. Studies have documented microplastics in the digestive systems of deep-sea fish, crustaceans, and invertebrates, even in regions far from land. Because food is scarce at depth, organisms are less selective, increasing the likelihood of ingesting non-nutritional material. Once consumed, microplastics can move up the food web, potentially accumulating in predators over time. Scientists are still working to understand the full biological effects, but concerns include physical blockage, chemical exposure, and altered energy intake. In an environment where efficiency is essential for survival, ingesting indigestible material introduces new stress. The presence of microplastics shows that pollution does not remain confined to the surface. It becomes woven into biological systems, even in the darkest parts of the ocean. Isolation does not protect the deep sea from surface activity, a reality that has become increasingly clear as research expands. The deep ocean is connected to the surface through sinking particles, circulation patterns, and biological movement. What happens above eventually influences what happens below. Pollution released near coastlines can spread across ocean basins, settling into sediments or entering food webs far from its source. Noise, chemical contamination, and physical debris all travel downward or outward over time. Scientists often emphasize that the deep sea should not be thought of as separate from the rest of the planet. It is part of a continuous system, linked by processes that operate slowly but persistently. Distance delays impact, but it does not prevent it. The idea of untouched depths has proven to be an illusion, replaced by evidence that human activity now reaches nearly every corner of the ocean. Pollution at depth reveals a sobering truth about the reach of human influence. Plastics and chemicals descend into trenches, microplastics circulate through deep food webs, and isolation offers no real barrier against surface activity. The deep ocean absorbs what the surface releases, storing it quietly and for long periods. In a place defined by patience and slow change, pollution becomes especially persistent, reminding science and society alike that even the most remote environments are no longer beyond reach. Most deep-sea species have never been observed alive, existing only as traces, fragments, or preserved specimens lifted briefly into the light. For much of deep-sea science, organisms are known from nets, dredges, or sediment cores rather than direct observation. These methods can damage delicate bodies, erase natural behaviors, and remove animals from the context of their environment. As a result, scientists may know what a species looks like anatomically, without knowing how it moves, feeds, reproduces, or interacts with others. Many deep-sea creatures are so fragile that they disintegrate when brought to the surface, leaving behind incomplete clues. Even with modern cameras and submersibles, direct encounters remain rare. The deep ocean is vast, dark, and sparsely populated, making observation a matter of chance as much as planning. Marine biologists often note that entire lineages are known only from dead material, meaning that much of deep sea life remains functionally invisible. These species exist in a state of scientific anonymity, shaping ecosystems while remaining unseen in their natural state. New species are discovered on nearly every deep-sea expedition, highlighting how incomplete current knowledge remains. Whenever researchers explore a new area, sample sediments, or deploy cameras at depth, unfamiliar organisms frequently appear. Some are large and striking, while others are small, subtle, and easily overlooked. In many cases, these discoveries are not confined to exotic locations. Even regions thought to be relatively well studied continue to yield new species when examined more closely. Taxonomists working with deep-sea material often face the challenge of determining whether a specimen represents a truly new species or a known one displaying unexpected variation. This process can take years, requiring careful comparison and genetic analysis. The steady pace of discovery suggests that exploration has barely scratched the surface. Each expedition expands the known boundaries of life while simultaneously revealing how much remains unknown. In the deep ocean, discovery is not the exception, it is the expectation. Many deep-sea ecosystems remain entirely unmapped, existing beyond the reach of detailed observation or measurement. Large portions of the seafloor have never been visually surveyed, and even basic information about depth, terrain, and habitat type is missing for vast areas. Mapping the deep ocean is technically challenging and resource-intensive, requiring ships, sonar systems, and time. As a result, exploration tends to focus on specific targets rather than comprehensive coverage. Entire mountain ranges, valleys, and plains remain known only as vague outlines or not at all. Without maps, predicting where ecosystems exist or how they are structured becomes difficult. Marine scientists often emphasize that this lack of spatial knowledge limits understanding of biodiversity, connectivity, and resilience. Ecosystems may exist that have never been sampled, observed, or even suspected. The deep ocean remains one of the least charted regions of the planet, not because it lacks features, but because it lies beyond routine access. Technological limits restrict exploration depth and duration, placing practical boundaries on what science can currently observe. Submersibles and remote vehicles must withstand immense pressure, operate in complete darkness, and function reliably far from human intervention. Power supply, communication, and mechanical wear all impose limits. Even the most advanced systems can only remain at depth for limited periods before returning to the surface. Coverage is slow, and each mission requires careful planning and significant expense. These constraints mean that exploration proceeds incrementally rather than continuously. Many environments can be visited only briefly, if at all. Scientists must choose where to look, knowing that countless other locations will remain unexplored. As technology improves, these limits shift, but they do not disappear. The deep ocean remains resistant to rapid or comprehensive exploration, ensuring that large portions will remain unknown for the foreseeable future. Scientific estimates suggest that millions of species remain undiscovered in the deep ocean, a figure that reflects both scale and complexity. The deep sea covers the majority of the planet's surface and includes a wide range of habitats, from sediments and rocky slopes to vents and seeps. Invertebrates, microbes, and small organisms dominate these environments, and many are difficult to distinguish without detailed analysis. Statistical models based on sampling rates and known diversity consistently point to vast numbers of undocumented species. This does not mean they are rare or insignificant. Many may play essential roles in nutrient cycling, carbon storage, or food web stability. The sheer number of unknown species challenges traditional ideas about biodiversity, suggesting that Earth's biological richness is far greater than current catalogues imply. The deep ocean is not a marginal habitat. It is a central reservoir of life that remains largely unexplored. The unknown majority defines the deep ocean more than any single feature. Most species have never been seen alive. New organisms appear with every expedition, and entire ecosystems remain unmapped. Technological limits slow exploration, while estimates continue to expand the scale of what remains undiscovered. The deep sea is not simply poorly known, it is fundamentally underexplored, holding a vast living world that science is only beginning to glimpse, reminding humanity that the planet still contains realms where mystery outweighs certainty. The deep ocean plays a crucial role in regulating global temperature, acting as a vast buffer that absorbs and redistributes heat across the planet. While the atmosphere responds quickly to changes in sunlight and greenhouse gases, the ocean responds slowly, storing enormous amounts of heat within its depths. Water has a high capacity to hold heat, and the sheer volume of the deep ocean means it can absorb excess warmth without dramatic immediate changes in temperature. Much of the heat generated by recent surface warming has not remained in the air, but has been taken up by the ocean and gradually transported downward. Oceanographers often describe the deep sea as Earth's thermal memory, quietly moderating extremes by smoothing out fluctuations over long periods. This buffering effect helps stabilize climate patterns, reducing the severity of temperature swings that would otherwise occur. Without the deep ocean acting as a heat reservoir, surface temperatures would rise and fall far more rapidly, creating a planet that is far less hospitable to life as it exists today. Carbon storage in deep waters affects climate over centuries, making the deep ocean one of the most important long-term regulators of atmospheric carbon dioxide. At the surface, carbon dioxide dissolves into seawater and is taken up by plankton during photosynthesis. When these organisms die or are consumed, some of that carbon sinks into the deep ocean as organic matter, or dissolves into deeper waters. Once there, it can remain isolated from the atmosphere for hundreds or even thousands of years. This process effectively removes carbon from short-term circulation, slowing the pace of climate change. Scientists studying carbon cycles often emphasize that the deep ocean acts as a slow but powerful sink, absorbing more carbon than forests or soils over long time scales. Changes in how efficiently carbon is transported to depth can therefore have lasting impacts on climate. If less carbon sinks, more remains in the atmosphere. If more is stored at depth, atmospheric levels can stabilize or even decline, but only over long periods that unfold beyond a single human lifetime. Ocean circulation links surface and abyssal layers, forming a continuous system that moves heat, carbon, nutrients, and oxygen around the globe. This circulation is driven by differences in temperature and salinity, which affect water density. Cold, salty water sinks in certain regions, particularly near the poles, and begins a slow journey through the deep ocean. Over time, this water spreads across basins, eventually rising again in other regions through upwelling. This global conveyor connects the surface ocean, where weather and biology dominate, with the abyss, where conditions change slowly and predictably. Oceanographers often note that no part of the ocean is truly isolated. Even the deepest waters are part of a planet-wide circulation system that redistributes energy and materials. This linkage means that processes at the surface can influence the deep sea and vice versa. What happens in one region may take decades or centuries to be felt elsewhere, but the connection remains unbroken. Deep currents move slowly but persistently, shaping the ocean in ways that are easy to overlook but impossible to ignore over time. Unlike surface currents driven by winds, deep currents move at speeds that can seem almost motionless, sometimes only a few centimeters per second. Yet they flow continuously, year after year, century after century. Because they are driven by density differences rather than weather, they are remarkably stable. These slow movements transport cold water, dissolved gases, and nutrients across entire ocean basins. Marine scientists often compare deep currents to glaciers, advancing imperceptibly but exerting enormous influence through persistence. Over long periods, these currents determine where nutrients accumulate, how oxygen is distributed, and how heat is stored. Their slow pace means changes propagate gradually, but once altered, the effects can last for generations. In the deep ocean, speed is not required for impact. Consistency is enough. Changes at depth can influence surface life long after they begin, underscoring how deeply connected Earth systems truly are. A shift in deep water formation rates, for example, may not immediately affect surface temperatures, but over decades it can alter circulation patterns that influence climate, weather, and marine productivity. Similarly, changes in carbon storage at depth may take centuries to fully manifest in atmospheric concentrations. This delayed response makes cause and effect difficult to link in real time, challenging both science and policy. Oceanographers studying past climate transitions often find that deep ocean changes preceded surface shifts, acting as slow triggers rather than immediate drivers. The deep sea operates on timescales that stretch beyond human planning horizons, but its influence eventually reaches the surface. What begins quietly at depth can shape ecosystems, climate patterns, and life far above, long after the initial change has passed unnoticed. Earth's quiet engine runs far below the surface, powered by cold water, slow currents, and immense scale. The deep ocean absorbs heat, stores carbon, links distant regions, and moves energy patiently through the planet's systems. Its currents are slow but relentless, its impacts delayed but profound. While it rarely draws attention, the deep sea plays a central role in maintaining a stable climate and a livable world. Understanding this hidden engine reveals that much of Earth's balance depends not on rapid change, but on the steady, enduring processes unfolding in darkness beneath the waves. The deep sea reminds humanity of its limited reach in a way few other environments can. Despite satellites, global communication, and advanced technology, most of the deep ocean remains beyond routine access. Human presence there is brief, mediated and fragile, dependent entirely on machines that must withstand crushing pressure and total darkness. Even then, exploration is slow and selective. A single descent reveals only a tiny fragment of a vast world. This reality quietly challenges the assumption that modern humanity has mastered its planet. The deep sea exists largely outside daily awareness, yet it covers more of Earth than all continents combined. Scientists often reflect on how little direct experience humans have of the environments that dominate the planet. The deep ocean is not hostile out of malice, but indifferent to human needs. It does not yield easily to curiosity or ambition. In confronting its scale and inaccessibility, humanity is reminded that technological capability does not equal omnipresence. There are still realms where reach is limited, knowledge is partial, and humility remains appropriate. Most of Earth exists beyond direct human experience, and the deep ocean embodies this truth more clearly than any other place. Daily life unfolds on land and at the surface of the sea, creating the impression that these zones represent the planet as a whole. In reality, they are thin layers atop a much larger system. Below them lies a world of immense volume, persistent darkness, and slow processes that shape global conditions without ever being seen. Humans can map, model, and sample this environment, but they rarely encounter it firsthand. As a result, understanding often relies on indirect evidence and inference rather than direct observation. This distance influences how the planet is perceived. It is easier to value what is seen regularly than what exists far below awareness. The deep sea challenges that bias, revealing that Earth's dominant environments are not those most familiar. Recognizing this imbalance reshapes perspective, emphasizing that human experience represents only a narrow slice of planetary reality. Life thrives under conditions once thought impossible, and the deep sea has repeatedly forced science to revise its assumptions. Extreme pressure, near freezing temperatures, complete darkness, and limited food were once considered barriers to complex life. Yet exploration has revealed thriving ecosystems adapted to precisely these conditions. From hydrothermal vents powered by chemical energy to trenches supporting organisms under immense pressure, the deep ocean demonstrates that life is remarkably flexible. Each discovery expands the known boundaries of biology, showing that survival does not require warmth, light, or abundance. Instead, it requires adaptation. Scientists studying these systems often note that what was once labeled inhospitable is now understood as simply unfamiliar. The deep sea does not represent the edge of life's capability, but one of its most compelling expressions. This realization alters how environments are evaluated, both on Earth and beyond, replacing narrow definitions of possibility with evidence grounded in observation. The deep ocean reshapes definitions of habitability, influencing how scientists think about life across the universe. If complex ecosystems can exist without sunlight, fueled instead by chemical energy, then the range of environments capable of supporting life is broader than previously assumed. Worlds once dismissed as barren, such as icy moons with subsurface oceans, now appear more plausible as potential habitats. The deep sea provides a working model for how life can persist in darkness, isolation, and extreme conditions. It shows that habitability is not a single set of surface-friendly criteria, but a spectrum shaped by energy availability and time. Astrobiologists often point to deep-sea environments as analogues for extraterrestrial systems, using them to test ideas about life beyond Earth. In this way, understanding the deep ocean extends far beyond marine science. It informs how humanity searches for life elsewhere, grounding speculation in evidence from its own planet. Understanding the deep sea reshapes how Earth itself is understood, revealing it as a system driven by slow, interconnected processes operating far from view. The deep ocean regulates temperature, stores carbon, preserves history, and sustains ecosystems that influence the surface indirectly but profoundly. Its scale and persistence challenge short-term thinking, emphasizing timescales measured in centuries or millennia rather than years. When the deep sea is considered, Earth appears less like a static backdrop and more like a dynamic layered system where unseen processes matter deeply. Scientists increasingly recognize that many global changes cannot be fully understood without accounting for what happens at depth. The deep ocean is not a distant curiosity. It is a central component of the planet's functioning. Perspective and scale emerge naturally from studying the deep sea. Human reach is limited, experience is partial, and assumptions are often challenged by evidence from below. Life persists under conditions once deemed impossible, reshaping definitions of habitability and expanding understanding of Earth and beyond. The deep ocean does not simply add detail to planetary knowledge. It reframes it, reminding humanity that the world is larger, stranger, and more resilient than surface experience alone would suggest. The deep sea is not a separate world hidden beneath the surface. It is the largest, oldest, and most enduring part of Earth itself, shaping the planet quietly and persistently while remaining mostly unseen. Everything explored so far points to the same truth. What lies beneath the waves is not empty space, not a barren abyss, but a living system that operates on timescales and principles very different from everyday human experience. Darkness, pressure, cold, and distance are not obstacles to life here. They are the conditions that define it. Across immense depths, sunlight fades and disappears, yet life continues without pause. Energy arrives slowly, either drifting down from the surface as marine snow or rising from the planet's interior through vents and seeps. Food is scarce, irregular, and precious, and life responds by slowing down. Growth stretches across decades. Lifespans extend far beyond human expectations. Movement becomes deliberate. Bodies soften, simplify, or stretch into unfamiliar forms that conserve energy and tolerate pressure. In the deep ocean, speed is rarely rewarded. Endurance is. Bioluminescence replaces sunlight, turning darkness into a language of flashes, glows, and signals. Light becomes a tool for hiding as much as for revealing, for luring prey as much as for avoiding it. Sound travels farther than vision ever could, carrying information across vast distances. Vibrations replace sight as the primary way many animals perceive the world. Even silence is never truly empty. The deep ocean hums with distant earthquakes, shifting ice, slow currents, and the movements of living things, forming an acoustic environment that connects places separated by hundreds or thousands of kilometers. The seafloor itself tells a story written over millions of years. Plains smoother than deserts stretch endlessly. Trenches mark places where the planet folds inward, recycling its own surface. Sediments accumulate grain by grain, preserving records of ancient climates long after surface traces vanish. Tracks and burrows reveal constant activity in places that appear still. Life is present even where it is rarely seen, leaving signatures rather than spectacles. Invertebrates dominate this world, not because vertebrates failed, but because flexibility, softness, and efficiency offer advantages under pressure. Worms, crustaceans, mollusks, and microbes perform most of the work that keeps deep-sea ecosystems functioning. They recycle nutrients, process carbon, build habitats, and support food webs that operate patiently and persistently. Many of these organisms remain unknown, undescribed, and unseen alive. Entire ecosystems exist beyond maps, beyond cameras, beyond names. Time behaves differently in the deep ocean. Corals grow for thousands of years. Chemical signals remain stored in water and sediment for centuries. Changes unfold slowly but last a long time once they begin. The deep sea remembers. It records climate shifts, circulation changes, and biological patterns that surface environments forget through erosion and disturbance. This long memory makes the deep ocean both a stabilizing force and a delayed responder. It absorbs heat and carbon quietly, buffering the planet against rapid change. But when its balance shifts, the consequences can echo upward long after the initial cause. Human presence in this environment remains limited and fragile. Entry requires specialized technology that briefly recreates surface conditions inside rigid shells. Manned dives are rare moments of direct encounter. Most observation now comes from robotic explorers that descend silently, gathering data piece by piece. Even with these tools, knowledge grows slowly. Every expedition reveals something unexpected. Familiar species behave in unfamiliar ways. New organisms appear where none were predicted. Entire communities emerge around chemical energy sources once thought irrelevant to life. At the same time, human influence reaches the deep sea more easily than humans themselves ever could. Plastics settle into trenches. Chemicals bind to sinking particles and accumulate in sediments. Microplastics enter food webs where efficiency is already stretched thin. Noise travels downward, altering soundscapes shaped over millions of years. Resource extraction is considered for minerals that took geological timescales to form. Disturbance may persist longer than civilization itself, while scientific understanding struggles to keep pace with industrial interest. This contrast is one of the most striking lessons of the deep ocean. Human reach is limited in presence but extensive in impact. Distance delays consequences but does not prevent them. The idea of untouched depths has given way to evidence that no part of the planet is truly isolated. The deep sea absorbs what the surface releases, storing it quietly and for long periods, whether that input is heat, carbon, or waste. Perhaps the most important insight offered by the deep ocean is one of perspective. Most of Earth exists beyond direct human experience. Daily life unfolds on land and at the surface, creating the illusion that these zones define the planet. In reality, they are thin skins atop a much larger system. The dominant environments are dark, cold, high pressure, and slow. Life thrives there not despite these conditions but because of them. This realization reshapes how habitability itself is understood. The deep sea shows that complex ecosystems do not require sunlight, warmth, or abundance. They require energy, time, and the ability to adapt. Chemical energy can replace solar energy. Stability can replace productivity. Cooperation can replace competition. These lessons extend beyond Earth, informing how life might exist elsewhere in the universe. Worlds once dismissed as lifeless now appear plausible, not through speculation, but through evidence drawn from Earth's own depths. Understanding the deep ocean also reshapes how Earth is understood as a system. Climate, circulation, and biology are inseparable from what happens at depth. Heat absorbed today may influence weather decades from now. Carbon stored in deep waters may shape atmospheric composition centuries into the future. Changes that begin quietly below may surface long after their origin is forgotten. The deep sea operates on timescales that challenge short-term thinking. reminding humanity that planetary processes do not align neatly with political cycles or economic plans. There is no single defining feature of the deep ocean. It is not just dark, not just deep, not just cold. It is a complex, layered system where life persists patiently, energy moves slowly, and history accumulates rather than erodes. It is both resilient and vulnerable, stable and sensitive, ancient and still changing. To study the deep sea is to confront scale, in space and in time. It reveals how small human experience truly is relative to the planet as a whole. It shows that much of Earth operates beyond sight, beyond sound, beyond immediate consequence. And yet it also shows that this hidden world is not distant from daily life. It regulates climate, stores carbon, supports biodiversity, and absorbs the impacts of surface activity. The deep ocean does not announce its importance. It does not demand attention through dramatic change or visible landmarks. Its influence is subtle, cumulative, and persistent. It works quietly, steadily shaping the conditions that make the surface world livable. In doing so, it offers a different way of understanding Earth, one grounded not in speed or spectacle, but in endurance. In the end, the deep sea is not defined by what humans have explored, but by what remains beyond reach. Most species are still unknown. Most habitats remain unmapped. Most processes unfold unseen. This is not a failure of science, but a reflection of scale. The deep ocean is vast enough that mystery is not an exception. It is the norm. To understand the deep sea is to accept that Earth is larger, older, and more complex than surface experience suggests. It is to recognize that life adapts in ways that challenge intuition, that time stretches far beyond human planning, and that the planet's most important systems often operate quietly, out of sight. The deep ocean does not ask to be conquered or fully known. It asks to be understood slowly, carefully, and with humility. It stands as a reminder that Earth is not only the world humans inhabit, but a much larger system that existed long before humanity and will continue long after.